Hey guys, this is my very first numerical methods video, and here we discuss Newton's method. So I guess I should take the time now to let you know the basic layout of the videos for numerical methods. So the videos here will involve a concept or a theory video like this one, which will invariably have a purple background, and then I'll follow the theory with a Mathematica programming example. So in other words, like once I finish this video, then I'll show you how to program Newton's method using Mathematica so that you can use it to estimate zeros of functions to a degree of accuracy that you like. Yeah? Cool. So that's how it goes. Or that's how it's going to go. Cool. Now, what is Newton's method? Well, and what does it do? First, what it does is estimate zeros, clearly, by the title, right? But how does it work? Well, it assumes that your curve or your function is differentiable. And these are supposed to be x and y axes. So yeah, y and x here. And so once you assume that the function is differentiable, let's say that you're trying to estimate the zero here. And let's say that that zero is like a. Yeah? Cool. So then, notice that a tangent line in the neighborhood of a would give a very good estimate of the zero at a. For instance, let's say that you draw a tangent line at this point right here, which is pretty far from a, this point right here. Then the tangent line would look something like this. Let's see, what color suits a purple background? This is good enough. So the tangent line there would look like that, right? Okay, cool. Now, let's say that this point here, its x coordinate is x1. Fine. x1 is somewhat near a, and so we're going to use a tangent line at x1 to this curve, and let's say that our curve is f of x, as it's almost always called, right? When it's available, when the choice of f of x is available. Anyway, yeah, let's say our curve is f of x, and so you're trying to estimate the zero of f of x, specifically the zero that is a, using the tangent line at x1. Notice that the tangent line at x1 will say that your zero is like right here. Like, let's say that that's b. Not bad, right? It's not a, but it's pretty close. And as I'll show you in Mathematica, once we get the formulation of Newton's method, you can create an iterative process. Sorry, I mispronounced that. But yeah, you can create an iterative process that will improve this guess of b repeatedly. And this is kind of how it's going to improve it, right? Like, so in Mathematica, what you're going to do is you're going to see let's say that b is actually called x2. Then you're going to, at the end, once you figure out what b is, you're going to try and evaluate the value of the function there. Clearly, f of x2 is not 0. It's like right here. It's pretty near 0, but it's this value. But you want it to be 0. So what you're going to do is you're going to replace x1 with x2 and then repeat the process. Now use a tangent line at x2 to guess your 0 at a. So this time you'll have something like that, right? And it's getting closer to a, and then you get it. You'll repeat this process, and that way you could get an estimate of a that is as close to a as possible, as close to a as you'd like. Not possible, but as close to a as you'd like, because you could just set a requirement that the function's value at whatever is claimed to be your 0 be like as close to 0 as you'd like, so that it's actually a 0 of f of x, right? Cool. So that's basically the gist of how Newton's method works. So, to create the iterative process, we need kind of like what it is that we're iterating. We need like a formula that we can use for the iterative process, and that's what we're gonna do in the rest of this video. In other words, we're gonna try and figure out what b or x2 would have to look like using that tangent line that we've drawn in green or neon. I'm not good at colors. Okay, so what's the equation of this tangent line? Well, being that the point there is x1 comma f of x1, we know from calculus that the tangent line would be y minus y1, which is f of x1, y minus y1, which is f of x1, equal m, the slope, and the slope at x1 is f prime of x1. Now you see why we require that the curve be differentiable. It's not f prime of x, but f prime of x1 times x minus x1. Now, immediately notice that there are only two variables, this and this. And the tangent line here is y equals, and we can get it to be an mx plus b form, but the point slope form suffices. But if we want to know where that tangent line hits the x-axis, in other words, if we want to know where b is, we need to make y 0. So let's do that. When we make y 0, right, the equation says negative f of x1 is equal to f prime of x1 times x minus x1. Clearly, the only thing there is to solve for is the 0, and the 0, which is b, right, our estimate of the 0 anyway, which is b, is going to be like solving for this x, right? Okay, so let's solve for that x. Well, it's clear that our first move should be dividing by f prime of x1 on both sides, right? Yeah. Notice it says f of x1. Well, negative f of x1, but it doesn't say f prime. I don't want you to think that we have to write a 1 on the left side. F prime of x1, it's easy to mix it up. Okay, cool. And of course, what that'll let us do is it'll let us get rid of this and this. So now we see that x minus x1, I led with x, my x1 rather, but x minus x1, this is going to equal that right there. And we're almost done solving for our 0, which is b. So, or our estimate of the 0, I should say. And obviously, to find our estimate, and let's say that our estimate is this, renaming that, right? Okay, is going to equal x1, and then that already copied and pasted. Yep, there you go. Although this x1 is really poor. So, yeah. Okay, didn't let me. I guess I can improve it like that. Okay, fine. So this is what we are going to use in our iterative process in Mathematica. But yeah, there we go. So our estimate for a, the actual 0 of the function, is right there, which is the right-hand side. Yeah? Cool. And obviously, as I said, in Mathematica, you'll see that what we're going to do is replace x1 with this, and then repeat the process. Yeah? Cool. Take care.